So we would have been looking at heat capacity for some time. We started out looking at heat capacity, and then we went on to look at the heat energy required to change the temperature of a specific mass of a substance, specifically 1 kilogram, right? Which we would have related as our specific heat capacity. So now, we would have seen hopefully from discussing the concept of heat capacity, we would have seen that when we apply heat energy to a substance, there's usually a change in its temperature, okay? So we would have seen, right, when we talk about heat capacity, that when we apply heat energy to a substance, there is an associated change in temperature. Now also, if you think back to when we had done a particular lab, right, to find the maximum and minimum temperature of water, right, you would have seen that we would have obtained a minimum temperature, which indicates the lowest temperature that you're going to have for water. And would have also obtained a maximum temperature, which would indicate, okay, the maximum temperature that water will attain. Now, again, we just said that when we apply heat energy to a substance, we will associate, or we will actually notice a change in temperature, okay? But in terms of the water, let us say that with the water, we would have heated the water, so we apply heat energy. The water would have started out at some initial temperature. Anybody remember measuring the initial temperature of the water? What you got? About what? Well, from the heat maximum minimum temperature lab, you'd have got about what? 30, right? About 30, right? Which is standard room temperature, okay? So you'd have applied heat energy from out of the water to the water, from it was at 30 degrees Celsius, and it eventually reached up to a value of what? 100, right? Most persons got 100, right? Now, you will notice that when we were doing the experiment, we had the water on the tripod stand, and we were constantly applying heat, because when it reached 100, we did not stop. It was still being heated. But each time a new group came up, they got the same temperature. So what's happening in that case? What's happening in that case? Because we're applying heat energy, but there was no change in temperature. It reached its maximum, right? Huh? Some person might get 101, a little bit. But for the most part, it was remaining at a certain value, even though we're applying heat energy. Okay? So, again, we want to know what's happening in that scenario. Now, if we think back to the scenario with the water, you probably would have noticed that there was something coming off the water. Steam, right? You'd have noticed steam or water vapor. Now, that water vapor now is a what? In terms of a state of matter? Gas, right? So we have gas coming off. So we add liquid, right, at 100 degrees Celsius. We apply more heat energy, and we get what? Gas. So the liquid, therefore, now was going through near. The liquid, therefore, was going through a change of state, right, or a change of phase. So what we see then now, students, is that when we have matter, say again? Oh. Okay, well, it's going to take some time, but I'm going to come back to your suggestion right now. So again, back to the hot water, ladies and gentlemen. Back to the scenario where we have the water at 100 degrees Celsius, and we continue to apply heat, but there was no change in the temperature. Okay? Even though we're applying heat, there was no change in temperature. However, we noticed that the liquid would have changed to vapor, or go from the liquid phase to the gaseous phase. Now, what we see now is that in order for that to happen, it requires energy, right? It requires energy in order for us to go from the liquid to the gas. So what we see then now is that whenever we experience a change of state, it's going to require energy. Okay? But that energy is not going to be manifested as a change in temperature. It's going to be observed as a change of state. Now, we could also observe that in terms of ice, which is a solid, right? If you get some ice, let's say, and you measure the temperature of that ice, it's going to remain at a constant temperature, right, of 0 degrees Celsius. The only way it will actually start to change is when you go to liquid. And we're going to have examples, where we actually see that. But again, what I want us to get from here is that once, we're going to come to you next, once we go through a change of phase, it's going to require energy. But the energy used to cause a change of phase, it will not manifest as a change in temperature. Okay? So what we see then, our bottom line is that a change of state or a change of phase always occurs at a constant what? Temperature. Okay? Okay? Yes. The condensation. You see the condensation because ice is so cold, the air, right? The air around it, it's starting to condense and create that little vapor thing. Yes. Yes. Good. Yes. Right? So the question over here was that if we had the water at 100 degrees Celsius, if we leave the Bunsen burner under the water and we're still supplying heat energy, if the temperature would remain at 100. And yes, it would remain at 100 until all the water turns into vapor. Now, that also now is the same reason, students, why when you're cooking, because if you cook and let's just say you boil and the steam, right, and it burn you, right? Right, the steam and it burns as if it is burning you very hot or hotter than the actual water. And that is because the steam that is produced, right, it can be at a higher temperature than the temperature of the water. Because again, the steam now is in the gaseous phase. Alright? So we're going to look at the concept of change of state. Alright? So we're going to talk about phase change. Alright? Phase change. And then later on we're going to talk about the heat associated with a change of phase. So what we're going to say now is that in order for a substance to undergo or to experience a change of state or change of phase, or a change of phase, and by change of phase we usually just mean it's changing state, right? Because we talk about states of matter, right? Matter exists in different states, and we can refer to those states as initial or individual phases, right? So in order for a substance to experience a change of phase, a change of phase, energy must be, we're going to say, added or removed. All right? So energy must be added or removed. So if we want to change, let us say, from liquid to gas, we have to apply heat. Similarly, if we want to change from, let's say, solid to liquid, we have to apply heat. But if heat, solid to liquid, you have to apply heat, because if you have a piece of rubber, you have to apply heat to melt it. Right? And if you want to do the opposite now, so let's say you have the vapor, and you want to get back liquid, you have to do what? So to go from liquid to vapor, we have to supply heat, or we have to add heat. So if we're going from vapor now back to the liquid, we have to do what? Cool, right? And by making it cool, we're basically removing heat, right? So when we remove the heat, it can go from the vapor to liquid. Similarly, if we have liquid, let's say some water, and we want to make ice, which is a solid, we have to place it in the fridge, and the fridge will basically remove heat from the water, and then that is how you're going to get your ice. So your fridge works by just removing heat from the substance. That is why the temperature decreases, and if you remove enough heat, it can actually cause it to become a solid. Okay? So we must add or remove heat. Now, when we remove or add heat, when we add or remove heat, this heat energy is used to make or break bonds. Right? Used to make or break bonds. So, energy associated, it is used to either make bonds or break bonds. Now, therefore, we observe a change of phase occurs at a constant temperature. Right? So, if you don't understand or don't get anything from this or from today's lesson, I want at the very least that we appreciate that whenever there's a change of phase, it will always occur at a constant temperature. Right? So a substance will change state when the temperature is constant, or only at a constant temperature we observe that change in phase. Now, after it would have transitioned from one phase to another, then we can see the temperature changing again. Okay? So once you're going through a change of state, it always occurs at a constant temperature. Now, as soon as we would have moved over from one phase to another, then we can see the temperature increasing, okay? Or decreasing, depending. So, a change of phase always occurs at a constant temperature. And again, we said that we need heat energy, right? We need heat energy in order to facilitate that change of state. And we're going to see if we can talk about that specific heat energy, right? So we observe a change of phase occurs. So we observe. I guess if we say observe that here, so that a change of phase occurs at a constant temperature. Right? So if you want to put that in, you can put that in. We observe that. Right? A change of phase occurs at a constant temperature. So, yeah, good to that as well. Right? Always occur at a constant temperature. Alright, yes. So, again, Sandy, we're saying that we are using heat to cause a change of phase, right? Or a change of state, right? So either we're adding heat or we're removing heat. So, normally, when we relate, Akila, when we relate the condition of applying or adding heat or removing heat, we always associate it with a change of temperature. But in this case now, we're saying that because the substance is going through a change of phase, we don't observe a change in temperature, right? Because the heat energy is not used to raise or lower the temperature. It is used to make or break bonds, right? So the temperature remains constant while the substance is going through a change of phase. Now we're going to talk about the heat energy associated with a change of phase. So we're going to move into a thing called latent heat. Huh? Okay. Oh. So, latent heat. So, when we talk about latent heat, we associate the heat energy required for a change of phase as the latent heat. Now the word latent, it is actually a Latin word, right? So latent heat is a Latin word which means hidden, right? Hidden. Because again, as we said, when we apply heat energy, we usually notice that there's a change in temperature. Now in this case, now because we're applying heat energy, when the substance is changing phase, and we're not seeing a change in temperature, we refer to that as a latent heat or a hidden heat. Okay? Because we don't see it in terms of the temperature changing. Okay? We only observe it due to the change of phase. You understand? Okay, so in this case, now we're talking about latent heat, which is considered to be hidden heat, because it is not manifested. So we're applying heat energy, but we don't see a change in the temperature of the substance. We see a change in phase. So we term it the latent heat. Okay? So we say now that latent heat, that this is the heat energy associated with a change of phase. Right? So latent heat is the heat energy that is associated with a change of phase. Now, we can define the latent heat. Right? So let's look at a definition. Let me just continue right there. The latent heat is defined as the heat energy required to change the phase or the state. Let me use the term state. We use them interchangeably. Change the state of a substance. Right? That's the latent heat. It's the amount of heat energy required to change the state of a substance. Now, we're going to go into further details and talk about a specific latent heat associated with a change from solid to liquid or vice versa. And we're going to look at a specific latent heat associated with a change from liquid to vapor and vice versa. So, let's go into the specific latent heat now. Specific latent heat. All right? So, specific latent heat. All right? Specific latent heat. Yeah, what that formula? That's formula. Specific latent heat. So we're going to say that this is, and again, if you remember about specific heat capacity, right? I know we're talking about specific latent heat. We're going to see that when we talk about specific latent heat, we're going to talk about a specific mass, which is always, the specific mass is always what? When we're talking about specific heat capacity, what was the mass of the substance that we, 1 kilogram, right? So in this case, now we're going to refer to 1 kilogram right here. So this is the heat energy required to change to cause a change of state of 1 kilogram of a substance. All right? So that's a specific latent heat. The amount of heat energy required to cause a change of state of 1 kilogram of any substance. And we can write a little expression where we say that the heat energy, EH, is equal to M times L. Right? E is equal to m times L. So in this case now, we have EH, which is our heat energy, and this is measured in joule. M is the mass, and mass is measured in kilogram, and then now L now is the specific latent heat. And specific latent heat is measured in what unit? Who said that? Who said it? Joules? Joule per kilogram, right? In joule per kilogram, right? So latent heat is measured in, specific latent heat, sorry, is measured in joule per kilogram. Now, when we talk about specific latent heat, as I said earlier, we can talk about specific latent heat associated with a change from solid to liquid and vice versa, or we can talk about a change of state from liquid to vapor and vice versa. All right, so as you note that down, we're going to be looking at that shortly. All right, so that's the specific latent heat. I'm going to go over this side to talk about the specific latent heat of when you go from a solid to a liquid or vice versa. All right, so we're going to say specific latent heat of, we're going to call this one fusion. Right? Specific latent heat of fusion, and we can write it as so. Right? Specific latent heat of fusion. Right? Specific latent heat of fusion. So we're going to now define this now. So we're going to say that this is the heat energy required to convert 1 kilogram of a solid to 1 kilogram. And here we could add to this, because as I'm here, I remember this, at constant temperature. So add this in for me, at constant temperature. Because we have to be clear that the temperature remains constant when the substance is changing state. To convert 1 kilogram of a solid to 1 kilogram of liquid, right? And we could say without a change in temperature, right? Or we could just say simply at constant temperature. So let's say at constant temperature. At constant temperature. All right? So that's the specific latent heat of fusion. It's how much heat energy you need to convert, and again, specific latent heat of fusion, right, is the amount of heat energy needed to convert between solid and liquid, right? To convert 1 kilogram of a solid to 1 kilogram of liquid without a change in its temperature, okay? So that's what we have for the specific latent heat of fusion. And we can write an equation in the form of this over here for this one. So we get EH is equal to what? Huh? ML, right? MLF, right? MLF, right? Where LF just simply stands for the specific latent heat of fusion. So this is our expression right here. And we can write this as EH is the heat energy LF? Yeah, what do I write it? For the sake of everyone. Yeah, I know, but for the sake of you know? Heat energy in joule. M is the mass in kg, and LF is the specific latent heat of fusion. So that's what we see. Now, from this definition, we can form a definition for the specific latent heat of fusion of any substance. And we're going to try for water next. So take that down for me in the meantime. A unit, yeah, just see it. And this is measured in, same as that over there, joule per kilogram. All right? Joule per kilogram. So the specific latent heat of fusion is measured in joule per kilogram. If I have what? Specific latent heat, yes. Kilogram. All right. Because again, coming from the general formula over here, so. Okay? So, I'm going to now define the specific latent heat of fusion of water. Let me do it over here. And for your syllabus, you will be required to be able to define the specific latent heat of fusion of water. All right? And you also will need to be able to recall the value. All right? So, specific latent heat of fusion of water. Specific latent heat of fusion of water. So this is the heat energy required to do what? Required to do what? To convert, yes, convert what? 1 kilogram of what? A liquid, specifically water, right? 1 kilogram of water to 1 kilogram of what? 1 kilogram of what? Solid, right? Solid water is what? Ice, right? 1 kilogram of ice at 0 degrees Celsius. Okay? So, the specific latent heat of fusion of water is how much heat energy is required to convert 1 kilogram of water to 1 kilogram of ice at 0 degrees Celsius. And we should all appreciate that the specific latent heat of fusion, right, it's to go from liquid to solid or from solid to liquid. So in this case now, if we want to convert 1 kilogram of water to 1 kilogram of ice, we're going to have to remove some heat, right? A certain value, and we're going to see the value shortly. We have to remove a certain value of heat from that water to make it into a solid. But if we have 1 kilogram of solid now, we have to apply that same amount of heat energy so that it can go from a solid to what? Liquid. So the latent heat goes both ways. Solid to liquid or liquid to solid. All right? Now, the value for the specific latent heat of fusion of water, we're going to say the specific, let me just write it out as a symbol. So, LF for water, the value is 340,000, and the unit is joule per kilogram. Right? So in order for us to convert 1 kilogram of water, yes, 1 kilogram of water to ice, you need to remove this amount of energy. If you have 1 kilogram of ice and you want to melt it to form 1 kilogram of water, you have to apply this amount of heat energy. For each kilogram, that is. Okay? Yes, for water. Okay? Yes. Double that, right. If it's 4 kilograms, you quadruple and so on. All right, so that's what we see. 340,000 joule per kilogram. Okay? So let's try an example. Can we? Example time? No example, Sandy? This is good for you? You can see it on the exam and no for. Huh? I don't mean determine if you pass, Sandy. Really? No, I'm not going to take off mark if it's not justified. All right, so example. So again, Warburton. The L. Just write how you write it then. Just go like that and F. You can do that. Right? You don't have to do it. I just do it cursive because person might think says if it's 1F or so. So example. So let's say we say calculate the heat energy required to completely convert completely convert what mass of ice? What mass? 10 what? 10 grams? 10 grams. Huh? Conversion? I like to have the conversion so you know we're reminded of how to convert. 10 kilogram of ice to water at 0 degrees Celsius. Alright, so we want to know how much heat energy is required to completely convert 10 kilogram of ice, which is initially at 0 degrees Celsius, to water, also at 0 degrees Celsius. So, we start out by saying that EH is equal to MLF. Now, M is 10 grams, which we can convert to kilograms, right? We can convert to kilograms by dividing by how much? 1,000, right? No, I hear about, because some persons are not clear, I have to hold off a little. 1,000, so we get 0.01, right? Kilogram. So then, and we know that LF for water is always this number. Joule per kilogram. So, the mass is 0.01 kilogram times 340,000 joule per kilogram. So the kilograms will cancel off, right? And we get what? What do we get? Just joule, right? But when you multiply those out, what do you get? 3,400? 3,400? 0.01 times that, 3,400, right? So 3,400 joule, right? So we need that amount of energy in order to convert this mass of ice to water, okay? So if you take 10 grams of ice and you place it in an open container, and after a while you realize that the ice melts, right, to form water, and the temperature is at 0 degrees Celsius, it means that the ice would have absorbed this amount of energy from the environment, okay, in order to change its state. And again, notice that the temperature did not change because the substance was changing its state, okay? Yes. The answer means that, okay, the ice would have absorbed this amount of energy in order to form water. Okay? So after you take that done, I'm going to ask a very important question and see how we can answer it. All right, so we're going to, as I said, ask a question about this. So what we're saying is that in order for us to convert the ice, 10 grams of ice at 0 degrees Celsius to water also at 0 degrees Celsius, we require this amount of energy. So now, let me ask you a question. What if we are able to apply, let's say, 3,500 joule of energy to the ice? The 10 grams of ice at 0, we apply, let's say, 3,500 joules of energy. What do you think will happen? Huh? Yeah, so we have ice at 0 degrees Celsius, 10 grams. We apply 3,500 joules of energy. I know it's 3,400, but I'm just saying, let us say we apply more. It's going to melt. It's going to melt and evaporate. So if we apply 3,500, we're applying basically 100 joule more than what is needed to melt it. So what would that extra energy be used to do? Huh? I mean, it's going to heat the water and cause what? It's going to feel heat. But remember, when we apply heat energy, it is usually associated with what? A change of what? Well, phase, yes, here. But if we apply extra energy, right, above what is needed to change the phase, what will happen? A change in temperature. So if we apply 3,500 joules of energy, we're going to use this to change the phase, and the extra amount is going to use to raise the temperature. Okay? And we're going to look at an example where we're going to see that happening. Okay? Okay? So let's say we do one next example over here. All right, so, and oftentimes you will see these types of examples. So, let's say we do it this way. So, let's say that a container containing, or a container with, let's say 25 grams of ice is left in the open for, let's say, for, it doesn't really matter the time, but let me just put the time here because maybe I can pull off another question from it. For, let's say, for how long? For how long? Huh? Where? 5 minutes, okay, for 5 minutes. All right? For 5 minutes. And I'm going to just add this right here. At 0 degrees Celsius is left in the open for 5 minutes. Now, after 5 minutes, the ice has melted to form, let's say, water at, let's say, water at maybe, oh yeah, you know, so at 4 minutes, I think, good, all right, 4 degrees Celsius, all right, 4 degrees Celsius, all right, so this is what we have, all right, and then we're going to say, calculate the heat energy absorbed by the ice in order to melt the ice and form water at 4 degrees Celsius. So this is our scenario. And for these type of questions, we always like to sketch out a little diagram, Shanoya. We always like to sketch out a little diagram for these kind of questions, okay? And we're going to do just that. We're going to do just that. So as soon as you are able to catch up with this, then we're going to sketch out the diagram and discuss. All right, so when we are looking at these type of questions, we always want to visualize what's happening with the substance, right? We always want to visualize what is happening with the substance, because when we have the water at 0 degrees Celsius, it's not going to just immediately form water at 4 degrees Celsius. In order for us to get water at 4 degrees Celsius, the ice must first do what? Melt, right? To form water at 0 degrees Celsius. Then we're going to now take the water at 0 degrees Celsius and it's going to further absorb heat energy to form water at 4 degrees Celsius. So what we see now is that we have 2 steps taking place. So let's illustrate that. So let's say we have our container like this, right, with the ice. Let's say these are ice cubes, whatever, something like that. So we're going to have the ice cubes. It's going to melt. So we're going to have melting taking place. And we're going to have water being formed. Right? So this is going to be water now. Let me use the black, maybe. So now we have the water now. Right? And again, we started out with ice at 0 degrees Celsius. Right? We form water at what temperature? Now when we reach this size, remember, you're not going to go one step, 0. I hear Warburton was saying 4. So we're going to have, as 0 said? I hear 4. I hear 4 somewhere. Huh? Okay, I heard 4, sorry. So we have ice at 0, right? We're going to have melting taking place to form water also at 0 degrees Celsius. So we're going to have water here at 0 degrees Celsius. But again, remember, we're going up to 4. So it's going to absorb more heat energy. Right. Hold on, I'm soon talk to you. And we're going to get water here now. Same water, but the temperature is now 4 degrees Celsius. Yes. Mm-hmm. Yes. So the ice, the more temperature is going to increase. But before the temperature can start to increase, it has to melt completely. So we have to completely melt the ice to form water at 0 degrees Celsius before the temperature can start to increase. Yes, so right, so I'm showing you now that, okay, in this case now, this is needed to melt the 10 grams of ice. But if we leave it out, if we leave it out some more, it can absorb more heat energy that will cause the temperature to rise from 0. Okay? Yes. The contents is going to be at 0 degrees Celsius. Okay? Yes. So the water and the ice are going to be at 0. Because remember in the same lab, the minimum temperature, the water and the ice was at 0. Right? And the temperature remained the same. Right? Even though you're adding more ice, the temperature did not fall below 0. Okay? So, this is what we see right here. Yes? Mm-hmm. No. Water will not lose. We're not going to lose water. So we see that, we have 2 processes or 2 steps taking place. Again, students, we see 2 steps. So we're going to need energy for this stage, and we're going to need energy for this stage as well. So let's say we call this stage 1. So stage 1, and this one is stage 2. So we have two stages, stage 1 and stage 2, and we're going to need energy for both stages. So in this case now, because we have going from a solid to a liquid, there's a change of phase, right? So we can talk about the energy that is associated with this change of phase, which is from solid to liquid. So that's going to be a latent heat of fusion. So the energy right here is going to be related to the specific latent heat of fusion of this substance, which is the ice. So we can write then that the energy right here, let's say we call it EH. If I can write this, EH is going to be equal to MLF. Okay? So the energy right here is related to the specific latent heat of fusion. And again, we know that it's going to be latent heat because the temperature did not change. Yes. Yes, you might get this on an exam paper and you have to do this. So again, Wallace. So again, we know that it's a latent heat, Sandy, because there was no change in the temperature, right? But because we go from solid to a liquid, it's a latent heat of, specific latent heat of fusion, okay? Now in this case now, we'll go from 0 degrees Celsius to 4. So in that case, there's a change in temperature, right? There's a change in temperature, so we have to associate the heat energy right here with a change in temperature, right? Which is our M what? MCAT, right? MCAT. Right, so we get EH right here now is equal to MC delta T, right? MC delta T. So we have to work out energy right here, and then we'll find the total. I'm going to do it over there, so. So we're going to work out for stage 1 and then stage 2. So let's say stage 1. So for stage 1, we say that EH equal ML what? Yeah? MLF, right? Because it's fusion, right? Now, if we note down some variables, M is 25 grams, right? But we're going to convert it to kilograms by dividing by 1,000. So we get 0.025 or 0.025 kilograms, kilogram. Right? And LF is always 340,000 joule per kilogram, right? Once you're dealing with water. So now, just plug in the values then. So EH is equal to M, which is that. So 0.025 kilogram times 340 joule per kilogram. 17, 8.5, something. Yeah. And this would be joule. So we have 8,500 joules of energy for stage 1. So the substance has to absorb 8,500 joules of energy to go from here to here. Then now we can do stage 2. Right? Stage 2. So this was stage 1 up here, so. Stage 2 now. Stage 2 is MC delta T, right? So EH equal MC delta T. So now, the same mass, right? So we don't have to work out the mass again, but we need to know the change in temperature. But the change in temperature in this case should be pretty straightforward because we're going from 0 to 4. So it's going to be just 4, right? So that's 0 kilograms times 4,200. Remember this one, specific heat capacity, right, for water per Kelvin times 4 Kelvin. What's that now? 21, 14, 4 times 14, how much that? 4, 46, 420. So this is 420, like that, joule, right? So it needs 420 joules to go from here to here. So the total energy then now, somebody saying? Yes, you may go. So the total energy E is then going to be equal to 8500 joule plus 420 joule, which is 8920 joule. Right? So that's the total amount of energy needed. So we absorb energy to melt, to form water at 0. Then we absorb extra amount to raise the temperature. So again, in order for the substance to start to increase its temperature, it must completely change to a different state. So in this case, from solid to liquid. So that's what we see right there. Time? What's the time? Means that what? 26 minutes? Okay, all right. So I'm going to give you one example to work then. I will just call it a what? A day, all right? Our class. Yeah, because it's still a rest of class for the rest of the day. All right? So, so again, any questions with this? All we're doing is just compounding what we would have learned from before. Okay? We're still using MC delta T, right? We got introduced, Aquila, to the specific latent heat of fusion, and we associate it with energy, with some energy. And we now are now combining both of them now to actually perform our calculations. So that's what we see. Now, all right, so we're going to say question for you to do. So we're going to call this one your activity. So we're going to say that a physics teacher, like myself, converts, let's say, 40 grams of ice to, 40 grams of ice at 0 degrees Celsius to water at 100 degrees Celsius using an electric heater. Oh, teacher. Yeah, Mr. Teacher never write it. Teacher converts 40 grams of ice at 0 degrees Celsius to water. All right, I'm going to add a 0 right here. 400 grams. 400 grams, just add a 0. 400 grams, because 40 grams just seem very, very small. 400 grams of ice at 0 degrees Celsius to water at 100 degrees Celsius using an electric heater. The heater was 100% efficient and was operated for 5 minutes. 5 minutes. All right? And we're going to say our questions now. 1, calculate the total energy absorbed by the ice in this process. And two, we're going to say calculate power, or let's say now, calculate the rate at which energy is transferred by the heater. All right, so those are your questions.